This is a presentation presented by or prepared by Bacharach, and we're going to take a look at it, and it's going to be on carbon monoxide. I considered fresh air as an enemy and closed with extreme care every crack and crevice in the room I inhabited. Experience has convinced me of my error. I am certain that no air is so unwholesome as the air in a closed room that has been often breathed and not changed. Now, let's see who's given credit for that. Benjamin Franklin, way back in the 18th century. He realized that the tighter we make our homes, the more we possibly could be getting sick. And what are we doing today? Tightening our homes, and the incidence of sickness is going up. Have we learned anything? You be the judge. To have pure air, your house must be so constructed as that the outer atmosphere shall find its way with ease to every corner of it. House architects hardly ever consider this. So what they're referring to here is infiltration, the air finding its way into our homes. As it is, they built what pays best, and there are always people foolish enough to take the houses they build. And if in the course of time the families die off, as is so often the case, nobody ever thinks of blaming anything but Providence for the result. Ill-informed medical men aid in sustaining the delusion by laying the blame on current contagions. What they're saying there is, as we're going to find out, the symptoms of CO poisoning are flu-like symptoms. So when you go to the medical doctor, they say, well, you've got the flu, and in fact, you may have CO poisoning. And the medical profession may not be up to speed with the fact that you've been in a situation dealing with the HVAC equipment in a tight house. Reading on, once ensured that the air in a house is stagnant, sickness is certain to follow. Florence Nightingale, way back in 1859. Again, have we learned anything? You be the judge. Carbon monoxide awareness. Is it measurable? Did I measure it? Is it safe to leave the appliance or combustion system running or operable? Have I provided my customer with enough information to alert them to any hazards that may be present? Would it be safe for me or my family to live or work in this building? Certainly, if you don't test it and measure it, you really will never know. Always consult with the authority having jurisdiction about how much carbon monoxide is too much, how much carbon monoxide is allowed in flue gas samples. What are the approved methods for sealing test holes? Are there any local codes for the workplace? What are the licensing and continuing education requirements for my profession within this jurisdiction? So what is carbon monoxide? It's an odorless, colorless gas that will kill you. It not only will kill you, but the problem is, over a period of time, it is absorbed into the bloodstream, and it's simply not a matter of going outside and your blood outgassing the carbon monoxide. It takes time for that to occur, so you can be sick for a long period of time. So it is a deadly gas. How do you measure carbon monoxide? You measure it in parts per million. If you take 1 million ping pong balls, white ones, that's 1 million white ping pong balls, and you take one out, and you put one red one in, you will have 1 in 1 million parts per million. If you take 15 out and put 15 in, you're going to have 15 parts per million. That's how carbon monoxide is measured. Now there's two ways to measure carbon monoxide. One is known as air-free, which means there's no oxygen in it, and then there is carbon monoxide with oxygen in it. What we are concerned about is the air-free. We don't want the oxygen in it. So if you know what the carbon monoxide is with air in it, you go to this formula, do the calculation, and you'll come up with an air-free carbon monoxide reading. You could also use an instrument that will give you an air-free reading, but you need to check to make sure that the instrument you're using does in fact give you an air-free reading. It may not. It may give you a reading with air. If you have air and you need to know what it is air-free, you can go to a chart like this one. And for example, let's say you take a flue sample of in your furnace and the oxygen content is 5%. So get on the left-hand side till you come to 5%. You find that the carbon monoxide reading in the flue sample is 100 ppm. Go to the column for 100. Where the two cross, we see that the air-free CO is 131 ppm. A lot easier than doing the calculations. Well, where does carbon monoxide come from? Well, auto exhaust can be 60%. So in other words, the auto exhaust can be very high in carbon monoxide, especially in the older automobiles. Notice this particular home has an attached garage, and we're going to be looking at that situation in a few minutes. You go to the basement, sources there is going to be a furnace, the water heater. You go to the right-hand corner, you'll find the gas dryer. You go to the first floor to the right of the garage, and there's a gas range in the kitchen. And all the way to the right on the first floor is a fireplace. So there's lots of places for sources of carbon monoxide, potentially in a home. But auto exhaust, 60%. Here's an integral garage, the garage built right in. What if you were to start your car up on a cold morning because the garage is unheated and you didn't open the garage door? You would be flooding the garage with carbon monoxide. Here's that same basement. Notice that the ductwork is not sealed. The seams are open. If you have a return duct in this particular space, it's going to draw any gases that happen to be in that space into the return airstream. Here we see a smoke candle being used, and you can see that the smoke is being drawn into that return duct because the return duct has not been sealed. Here's the seam of that return duct. Again, the smoke is being drawn into it. Likewise, any fumes that might be in that particular garage. Here's an opening between the garage and the lower level of this house. There's no blocking, no sealant, and you can see the smoke is just being drawn into that space. So that simply means that that home is under a negative pressure, and any fumes out in that garage are going to be drawn into it. Here we can see an opening between the garage and the other side of the basement. Here's a tractor. The gentleman sitting on it is reading 134 parts per million. So the smokestack, exhaust stack is coming up right in front of him on the front of the tractor, and it's spewing out the parts per million of CO, and it's reading 134. Here's another situation. Notice where the exhaust comes out. That's not the problem. The problem is, where is the inlet coolant fan for the engine? Right behind the exhaust. So the exhaust comes out, sucked right into that engine on the coolant side, blows up around the engine, comes out right under the seat of whoever happens to be running that particular tractor. Now where it goes from there, who knows, but the point is, we thought we got the exhaust away from the operator when in fact we may not have. Here's a great one. Start your car up in the morning if you're at the motel, and you let it run 10-15 minutes right outside your room. And you have a fresh air intake on that particular system, sucking that fume right into that room, all those fumes. Another source of carbon monoxide is unvented appliances. Unvented appliances, and they're showing you a range here. Now, the AGA, the American Gas Association, back in 1927, that's 1927, set the standard for vented, this is unvented in front of you here, but a vented gas range, it was legal for it to spew out 400 ppm, 400 parts per million of carbon monoxide. Unvented, which this one is, unvented is allowed to spew out 800 parts per million. Tremendous amount of carbon monoxide, as you'll see in a little bit. So here you have a freestanding, unvented gas range in your home, and it's allowed to spew out up to 800 parts per million. This is a great picture in terms of what it presents to the consumer. If you look on the wall, the blue wall, just to the right of the center, you'll see a hanging, freestanding, hanging, unvented wall heater, space type heater. Great advertisement. Okay, let's go ahead and install this thing in the home, and the consumer has no clue as to what's going on with carbon monoxide. In addition to that, if you'll notice, right above the freestanding fireplace in front of the, to the left of the picture there, right above it, it says the fire escape ladder. That's almost hilarious. Fire escape ladder. Now, they have a fire in that freestanding fireplace there, and to the left of that, you'll see bottles of lamp oil. Wait a minute, bottles of lamp oil next to where we have an open flame with a fire escape ladder above it. Okay, somebody did a great job on this one. Now look at this fireplace. If you'll notice to the left of the fireplace, that black stuff, that's soot. Most definitely carbon monoxide. Look in the lower right-hand corner, soot just laying there. So much soot that it just crumbled and fell down on the bottom of the fireplace. If you look at the log holder there, right above the log holder, that black soot, tremendous amount of carbon monoxide being produced in this particular fireplace. Another source of carbon monoxide would be backdrafting of appliances. Notice the dryer. We have the dryer operating. We may have a fan on in a bathroom or kitchen. It's creating such a suction on the house that when the furnace is going to be running, in order to run the furnace, we need to get air. But notice what's happening. The air is actually coming down the chimney instead of the flue gas is actually going up the chimney. So were the furnace to be running, we would be dumping all of those combustion gases into the conditioned space. House under a negative suction pressure. Look at the base of this chimney. Not a pretty sight. Something tells me that that's not what it should look like at the base of a chimney. Do birds go down flues to die? I don't think so, but it looks like in this case this one did. A real crispy critter on this one. Great carbon monoxide poisoning. Now this looks innocent enough. A door in a hallway in an apartment complex. But what lurks behind the door is not pretty. We open the door. Several things we see. First of all, this is a downflow counterflow furnace, so the return is on top of the furnace. Notice above the door there is a return air grill, so that we have a central return bringing all the air from that apartment through that grill into the furnace area. Notice around the vent pipe at the furnace breaching or opening. See the black soot? That's carbon monoxide. Look at the first joint after the elbow. Black sooting, carbon monoxide. Now remember, this is on the suction side, the return side of this furnace. So whatever's going out of those fittings is going into the space. Notice here we have not only the furnace, but the hot water tank needing to vent as well. Are we going to get enough oxygen for combustion? I think not. Notice something else. Behind the vent pipe there on the return air coming in, there is another opening. I understand that the contractor did a temperature rise across the furnace and found that there was insufficient return air coming back from the space. So they cut a hole in right there, put a return grill to increase the amount of return air. Where? Right where the furnace cavity is, in the closet. Great idea. What's wrong with this picture? Well, what's wrong with it is it's a type B vent, a double wall vent pipe that goes 2 stories plus beyond that. So that's a long run for hot flue gases to go up. Don't think those hot flue gases are going to get out the top. They're going to condense, and the water's going to run back the pipe and rust out the bottom of the pipe, if they even make it all the way up there. Here's a great one. This is an equipment room. Look at the furnace to the left. You see the return air grill. At least it's clean. But coming off the top of that furnace is a plastic pipe, so that's a 90% furnace. Look to the furnace to the right. There's another plastic vent pipe. That's a 90%. Look to the right of that. We have a boiler. Now that's a barometric draft boiler because it has a draft hood up the vent pipe coming off the top. So we have 2 90% furnaces and 1 barometric draft furnace. Look how they're vented. We took the 90%, put it into a common vent with the barometric draft. There is no literature anywhere that will tell you that you're allowed to do that. Now, on the 90%ers, you're always going to have condensate. And notice on the bottom of the larger round pipe, just to the left of that copper pipe, is a drip leg. So I guess the water will just drip out of there as it runs down the chimney and into that pipe. Here's a great one. What's wrong with this picture? Well, we see the chimney with an extension on it to get the vent gases up higher above the roof line. But that T in the line there has a barometric draft control. Now, if this is gas, usually gas doesn't have one. If this is oil, you would have one, but not there. The location should be in the vent connector between the actual furnace and the chimney. So again, poor installation, incorrect installation, not even poor. Now this is a homeowner special. Now the homeowner realized that flue gases do rise. And notice, the only way he could get it to rise is if he took the top of the gas heater and flattened the opening where the air should come in. But wait a minute, he knew he needed air, so he left the end of the vent pipe there, that connector, open. Great idea. This is a great one too. Look at the rusting on the furnace pipe. You can tell that that thing has not been venting correctly when you see that much moisture rusting out the vent pipe there. One thing you can observe when you go to residences is the door around windows. Now when you see the dirt around this door, you know that the house is under negative pressure because the air is trying to get in, and we can see that. It's pretty obvious from the dirt tracking or streaking, if you will, on this door. So before you even open the door and go in to look at this system, you know there's going to be an issue. Here's panning in the basement. Pulled down the panning to look what's up in there, and besides the dirt, there's no sealant to seal the gases that could come in there, maybe from a garage or maybe from a laundry room, from the gas dryer, and what have you. With all due respect, you may have done your job correctly, but look what happened. The electrician came in, the cable man came in, the telephone man came in, and they all cut holes in our ductwork. So we want to seal ductwork. We seal it with a mastic, and we're using a fiberglass mesh here if the gap's more than about 1/4 of an inch. And we put the mastic on, and that's going to create a sealant. But I think this is a little bit overkill. Now, it certainly wouldn't hurt to seal the return sides on a system. Supply would not be as critical because the air is going to be pushed out, but on the return side, it would be a good idea to do that. And why in the heck we even sell this stuff? Look what this homeowner did. He went and bought the flexible vent pipe that probably should be used only on dryers, and even then, probably should not be used. Hard pipe it for less resistance. I love that sag there. That's going to be a great moisture collector. Great trap. I think the flue gases are going to come out of there correctly. Here's another one. Look at this 80% furnace, and we have a hot water tank. Follow the piping coming off the 80% furnace. Comes up to a Y, looks like a Y fitting. What about the hot water tank? Let's take a closer look at that. Okay, a 90-degree on the elbow on the hot water tank, a couple 45s on the furnace, and we're going to tee into a common vent. But look at the pipe coming from the furnace. See the rust marks on it? Can't be venting properly. Now, once we take off the pipe at the breeching, something tells me that doesn't look right. There just shouldn't be there. What you see should not be there. So we know it's not venting properly. Well, let's take a little bit closer look. And look at the venter motor here. At the bottom of the venter motor of the fan assembly, look how rotting and rusting it's getting. If you look down below the gas burners, actually right above them, that deflector there, it's getting rusted. And let's take a little bit closer peek. Look at the rust laying at the bottom of the furnace under the manifold here. Can we say not venting properly? Now we have a cracked heat exchangers. Look at the percentage of cracked heat exchangers, less than 1%. But yet the HVAC industry says, well, if there's carbon monoxide poisoning or carbon monoxide in a building, it has to be the furnace. It doesn't always have to be the furnace, but it's certainly something you want to take a look at. Here are some pictures of some cracks in some heat exchangers. Visually, we've taken them apart. You can see them. If you had not taken them apart, some of these cracks are difficult to find. Now, we're going to be using CO alarms in our residences and buildings, and we can also go in and use test instruments to determine CO. It says, why wait for the alarm or injury? Somebody gets sick before we do any testing. What the promotion here is that you take your carbon monoxide tester with you, turn it on before you go into the building. When you go into the building, you check the CO reading both before you go in the building and after you go in the building to determine what's going on, to see if the elevation of CO would set up the alarm in your mind. Let's take a look at UL approval. Now there are some dates here. 1992. In 1992, the UL approved CO detectors to alarm after 8 hours and sensing more than 15 parts per million. So if the alarm sensed 15 parts per million or more for 8 hours, it would alarm. So you'd have to be exposed for 8 hours before it would alarm. Now that's in 1992. Let's go to 1995. Notice now, 15 parts per million for no less than 30 days. So now it would not sound the alarm for 30 days at 15 parts per million. Can you say that the UL dumbed down the sensitivity of the CO detector? And I like the last one at the bottom of the screen. It says all alarms had to have a reset button that alarmed if 100 ppm or more is present for at least 6 minutes. Wait a minute. I love reset buttons. The alarm goes off, I just push the reset button. I just go about my business as usual. So that's not the smartest thing to have on a CO detector, is a reset button to turn off the alarm and just go about your business, when in fact you may be in a high environment of ppm of CO. In 1998 now, the UL said 30 ppm for 30 days. So that means you can suck more CO for the same 30 days, be sicker, be exposed to it more, and be safer. And this is UL now. Now we're going to take a couple minutes and read through this one here. The CO alarm standard, less is more. It says a revised Underwriters Laboratory standard for carbon monoxide detectors goes into effect for models manufactured beginning this month. New UL listed detectors, now called alarms, will be required not to sound for at least 30 days if only low-level concentrations of CO are detected. Nor should they respond before at least an hour has elapsed, when as much as 70 parts per million is detected, since that is considered a short-term exposure. The UL change may sound odd, but it affects convenience rather than safety. There it is, convenience before safety. And is expected to reduce the incidence of false alarms. It would seem to me that if a CO detector goes off, to me that I would think is not a false alarm. Something needs to be attended to. Now it says models conforming to the new standard may not be out for several months, but if you don't already have one, don't wait to buy one. What they just said there is that the older ones were better. The newer ones are dumbed down. Evidence of it on the previous screens. Now, home CO alarms may also be cross-sensitive to a lot of different things that are in your home. Now, Nighthawk, manufacturer of CO detectors, says that they are cross-sensitive to the following things, and you see if you can keep up with them. All of these things, they're cross-sensitive to. A lot of things in your home that could set off the CO detector. That's why they're saying they dumbed them down. Continuing on. And the list goes on. Notice carbon dioxide, they are also cross-sensitive to. Carbon dioxide now, not carbon monoxide. Carbon monoxide is what they're to detect, but they're cross-sensitive to carbon dioxide. In 1992, the standard was 1,000 parts per million of carbon dioxide. In 1998, they upped the ante to 5,000 parts per million to make them less sensitive to carbon dioxide now. What's the health effects of carbon monoxide poisoning? Gets into the bloodstream and you can't get it out. That's the bottom line. Symptoms of carbon monoxide poisoning. Now notice at 200 ppm on the right hand side, at 200 ppm, you're going to have a slight headache, you're going to feel tired, you're going to be dizzy, you're nauseous after 2 to 3 hours. Now wait a minute. I'm going to have the same symptoms if I have the flu. Yeah, I'll even have the same symptoms if I was out half the night drinking. So we got to know whether we're drinking, whether in fact it's carbon monoxide in the home, or in fact we have the flu. All right. At 400 ppm, you have frontal headaches within 1 to 2 hours, life-threatening after 3 hours. And you can see that as obviously the ppm goes up, death can occur a whole lot sooner. So the higher elevated ppm rated levels of CO is not good. So let's take a look at a few things here. ASHRAE, which is the American Society of Heating, Refrigeration, Air Conditioning Engineers, said 9 ppm is the maximum allowable concentration for continuous, that's 24 hours, exposure. ASHRAE states the ventilation air shall meet the outdoor air standard. So ASHRAE says 9 ppm. The EPA says 9, this level or lower, as an ambient air quality goal averaged over 8 hours. This outdoor air standard is exceeded in many urban areas due to a lot of exhaust. In other words, what they're saying is the outdoor air is actually higher than the indoor air as far as CO. Common action level. 9 ppm or more above what you measured outside is the most common action level in the United States by local authorities of jurisdiction for further testing. Some jurisdictions require fuel shutoff until the problem is diagnosed and corrected. So if you have 50 ppm outdoors and you walk in and it's at least 59 ppm or greater, there's some call for action. Now, BPI, Building Performance Institute, says 10 to 35 is a marginal level in reference to potential or foreseeable problems in some situations. Occupants should be advised of a potential health hazard to infants and small children, elderly people, and persons suffering from respiratory or heart problems. So what you see here in this statement is who's affected first. And most likely the most severe is going to be your infant, small children's, and the elderly person. The healthy male, female at 35 is not going to be affected nearly as soon as these two groups. That's 10 to 35. Now just remember, I said that in 1927 the AGA approved unvented gas ranges in your home at 800 ppm. Okay, let's read on. The EPA says 35, this level or lower, as an ambient air quality goal averaged over 1 hour. Common action level, 35 ppm is also a common action level for fire department or other emergency responders to utilize a self-contained breathing apparatus, SCBAs, when occupation of that environment is to be sustained by that responder. So what they're really saying is some fire companies, firemen won't even go into a building if it's elevated above the 35 ppm. And yet here's the range pumping out 800 up to approved. OSHA is 50 ppm over an 8-hour period. That's a standard working day, basically. BPI says 36 to 99 is excessive. Medical alert. Conditions must be mitigated. Ventilation is required. Always test garage spaces. Individually test combustion appliances. All repairs to be conducted by a qualified technician with proper test equipment. If you get up as high as 100 to 200 ppm, it's plain down dangerous. And you evacuate the building. And 200 plus ppm is extremely dangerous, universally accepted as an evacuation action level. So what are the numbers? They're looking like they're putting their hats on, like the 9 to 15 to 30 to 35. And anything above that, you better be in red alert. Get the heck out. Get the problem resolved. What standard do we encourage? That's, again, going back to BACRAC, and they're simply saying any increase in ppm from the outside to the inside, you better be looking for some problems. Where's the problem? This standard is also common to some federally and state-funded weatherization programs, as well as protocol to some private companies engaged in carbon monoxide testing. Any increase is a no-no, basically what they're saying. Elevated CO levels mean that carbon monoxide is being produced and there is a direct path for CO to reach the occupants of the building. That's basically a conclusion you make. It's there, it's getting into the space. Now the standards for CO levels in flue, and now this is the flue gas. American National Standards Institute says 200 ppm CO air-free. Now this is the air-free is the maximum concentration from an unvented space heater. So in other words, manufacturers can allow up to 200 ppm air-free CO from their appliance in the stack. That's the unvented space heater. AGA says 400 for furnaces now. So in our furnaces, it could be up to 400 ppm. That's in the flue now. ANSI Z21 says 800 ppm for gas oven emissions. Now, where do you test for it? You got to test the undiluted flue gases. If you notice where it says flue pipe there, that flue pipe, prior to that, right below it, has a draft hood under it. Right below that has dilution air. So the air from the space is coming in through that draft hood and diluting the actual flue gases. So we could not take our reading in the flue pipe because we would have diluted flue gases. We would need to take our sensing, putting our sensing detector back into the heat exchanger where it says flue gases are coming out at the heat exchanger location. Gas-fired ovens, obviously you would take it at the outlet where the heat's coming up out of the oven application. Atmospheric floor furnace, notice we're taking the combustion test, the CO test, prior to the draft test. So in other words, right where the heat exchanger exhaust gases are coming out of the heat exchanger. Atmospheric space heaters, atmospheric means that you're going to have a draft hood on it. You got to take the combustion CO test back into where the heat exchanger is located. Mobile home furnaces. Now you'll notice the vent pipe here. The combustion air is in some cases the combustion air is coming in to the outer pipe. The flue gases are going out the inner pipe. Now that's on the roof, so the only way really to test that would be to get up there and test it as it's coming out. Some of the mobile home furnaces will bring the air in from underneath the furnace. In other words, they'll have a vent pipe going to the outdoors, depending upon the design. So it's a little more difficult to get this particular reading. Here we have an atmospheric forced air furnace. We want to again go back into the three slots, the three oval slots. The implication there is that we're taking our sample back in there before we get the diluted gases from the draft hood. Notice this particular furnace, tremendous amount of carbon built up. Here we have a boiler, but notice where we take the combustion test. Combustion tests are taken before the draft hood. You can take your draft test at two different locations, but the combustion test, the CO test, has to be taken below that draft hood. Likewise, in a hot water tank, you'll notice there is about the third statement down on the right-hand side. It says the undiluted flue gas sample taken under the draft diverter in top of the fire tube. Let's take a look at that. Now notice where he's taking it here. He's taking a flue gas reading, a CO reading, actually in the diluted gases. It's reading 9 ppm. But now he's sticking the probe down inside where the gas is coming up before they're diluted. And you can see the probe at this location. That would be the correct location to stick the probe to get the undiluted gases. Here we have an 80% furnace. We have a double vent pipe. That would be a type B vent, taking the flue gases as it's coming out of the furnace there. You could drill a hole between in the two pipes. That would be acceptable. As far as I know, in most if not all jurisdictions, it's not going to be an issue. But when you're done, you should put some red high temperature silicon on there. And you know the customer's probably going to take their finger and peel that off. So I would probably wrap that with a silver tape, high temperature tape then around it. Not that it would need to be really high temperature, even duct tape, silver approved UL 181, to cover the holes so that the customer doesn't pick away at it. Notice here where we're taking the reading, and in this case it's showing 0 CO in that stack. Here is a 90% two plastic pipes, and we're taking the CO reading on the pipe on the left, which is the exhaust. You could go outside and take it where it exits. unless it's on a roof, or you could drill the holes and again silicone and tape around it. Here we see a actually an oil furnace, and they're saying taking the CO in the stack as it exits the burner, the furnace, before that draft diverter. Now, what do you do with your equipment? Care and maintenance. Well, the biggest thing when you're dealing with hot flue gas temperatures, you have moisture. And you're taking samples of that flue gases through your meter and the moisture will condense in it. So the thing you can do, 3 tips to maintain sensor life on your sensors are going to be keep it dry. The second tip you need to do is to keep it dry. The third tip, in order to extend your sensor life, is to keep it dry. So if you keep the equipment dry, it's going to last a while for you. Of course, if you have moisture in there and you put it in your cold truck in the wintertime, it's going to freeze it. So if there's any moisture in there, you need to take it out, get it cleaned out on every sampling that you take. Make sure that it's dry. Safety, yours and your customers. Is it safe for me to be working here? In other words, when you go into a space, I personally would carry my personal CO detector, have it on before I enter, let it on as I enter the building to make sure that it's safe for me to be working there. If it's not safe for me, you need to take action to get the occupants out. Is it safe for me to be working here? I don't think it is under these circumstances. Thank you.